morning. So as announced, I'm Jaak Monbaliu. It's the one who is doing the work. He is at the moment in Aalto doing the experiments. It's Aalto, and looking at wave in ice, wave attenuation, and ice breakup. Just to sketch the context, Arctic sea ice. We see that since the 70s that sea ice is retreating, and this is the kind of average position over a number of years. In the 1980s, around 2000, and nearly 10 years ago, and we see that the extent in September is getting smaller and smaller. That I think is evidence that climate change is indeed affecting our ice cover in the Arctic. That opens opportunities for navigation, having routes going across the Arctic, opens opportunities to do oil and gas exploitation, but of course also creates new threats because in these regions doing oil exploitation, doing gas exploitation, the risks there are as high as anywhere else, and we know what the impact is on the environment. So anyway, we cannot say if they will go there and exploit these things. All we can do is try to help in prediction, both for shipping but also for possible exploitation, so that it can be done at in a responsible way. Next to having an impact on shipping and so on, it also has an impact on the wave climate. Because here, and this is from simulations, but you could get the same picture from observations, from satellite observation, altimeter and scatterometer observations, is that over the years, this is about the last 25 years, that there is an increase. The red is an increase of significant wave height in centimeters per year, and also in terms of an increase in wave period, depending on the time of year, July, August, September. Increases in wave height also means that you have increases in possible wave breakup and wave penetration. Just to look at the mechanism to understand this, these waves, basically when they reach the ice edge, you will have some reflection, just like in normal coastal engineering structures, and part will be transmitted. In the transmission process, depending on the properties of the ice and depending on the properties of the waves, you will have a breakup. If you have a breakup, with these ice floes, they will start to move and they will hit each other and they will pack together and they will go on top and you will get overwash, all kinds of things. The other effect that you have is that if you have broken ice, that the wave penetration goes much deeper. There's the attenuation effects of a fixed cover, and broken ice is quite different. So you have less attenuation and your waves can propagate much further. In terms of, just to have an idea, in terms of wave ice interaction, there are not that many field measurements. It's not the easiest place to go and measure waves, and there were some experiments in the 80s and on the Arctic, and I think these are relatively recent experiments in the Antarctic region. There are some numerical models on different types, and there are some laboratory experiments. To give you a few ideas, And basically, what you get out of a number of these publications is that waves attenuate under the ice and more or less exponentially. It goes faster and faster, but you still feel it goes for hundreds of kilometers. It is quite a long distance that you have these wave penetration. What we wanted to do in this experiment, I said there, I will show a picture at the end. They just started. Looking at realistic ice, because doing that in a plume or whatever in the lab is also not so easy. How fast does it break up? What is the flow size distribution? Do you come to some kind of steady state? What's the difference between compact ice and broken ice? And there were some preliminary experiments in the ice flume at the University of Melbourne. They have a tank of about 40 meters long. They can cover it with ice, and they have a number of cameras and systems to measure the movement and to look at the behavior of the ice. And I'll show some pictures. And they run a number of experiments with monochromatic waves with varying steepness from 0.4 to 0.1. That's from very gentle to quite steep. And they played a bit with the wave period as well, from 0.8 seconds to 1.2 meter. No, that was too fast. This is, I was hoping that this movie would run, but let's see if it wants to run. Yeah. How is it done? You basically start from melted ice, then you cool down for about a day, then you freeze for about 5 hours. When you freeze the ice, it attaches to the sides, and of course you cannot do experiments when it attaches to the sides, so you have to have a bit of recovery at a higher temperature so that it can detach from the sides, so that you can do your experiments. Then you can do your experiments, and then you can start all over again. So if you look at the sequence, it takes typically 2 days to do one experiment. So it's a time-consuming business. Afterwards, you can do some processing, because you can look how the ice labs, there are some markers in the ice so that you can easily mark them. And then they have a video system where they play with different lights to look at the water surface and to be able to track the water surface. And then you see that you can follow the ice sheet. At some moment it breaks, and you see that the behavior of the water flow over the ice is different, and that you get some different interaction, and you see that it runs over the ice, and that the hydrodynamics of the water flow over the broken ice is quite complex, and I think it will be a challenge to ever model this. And what were the results? Just to give an idea, this here we have the amplitude of the image. It's basically looking at the water displacement. The green dot here is the amplitude of the marker. That's the ice displacement. And it's normalized with the wave amplitude, basically. That's the incoming wave amplitude. And then you see that for this here you go towards longer periods. This is the gentle approach, and here you go from the gentle, from the low steepness to the high steepness, and we keep the period constant here. And then you see an evolution that longer waves can break up the ice. You see that even for mild conditions, the waves are longer, and that you can break up the ice. Here you see the full ice covering with blue. Here you see the purple here and a little bit jagged with broken ice. And you also see that if you go and you increase the steepness, then you already get some flow overflow at the beginning. You need longer periods to have some breakup, and then you get full breakup in the final stage here. And then you see you increase the steepness even more. You even get some breakup at the edge because the impact of and you also see that the movement here is larger. The impact is much larger. The storm waves, so they can really break the edge easier. We get more breakage and also fully broken conditions at the end. There are some limitations to this study. That's why we want to move to Aalto. Only fresh water. As the flume in Melbourne cannot work with other than fresh water. It's only in one direction, and it's relatively small scale. In Aalto, it's a bigger flume. It's I think 40 by 40 meter. In principle, able to do directional waves, but the amount of time that we have in the flume or in the basin is too limited, and we will only do one directional waves. But we will do them with irregular waves, and we will do basically 5 times the same test, just to be able to have some statistics. As we have about 10 days access to the facility, 2 days per test, basically because you need the time to make the ice, and hope to do that 5 times and to be able to say something statistically. We get the same kind of flow distribution, because that's basically what we want, is to have compact ice over the facility, have some pressure sensors so that we can measure the waves, some motion sensors on the ice so that we can, with cameras, can track the ice motion, and then of course at the end you want to have the distribution of the ice, and you want to hope that the markers are all nicely on the patches so that you can really see the movement, or at least enough of them. And by repeating this experiment, we will be able to say something about repeatability, and hopefully at the next step can think of more extensive experiments. Yeah, getting there. So to conclude, a small scale experiment we have done. It gives a first idea. We could derive some conclusions, but we want to check them in a larger facility. The short periods, small steepness waves, they don't travel very far under the ice. They're damped quite easily, but longer and steeper waves, they go farther into the ice, and they're able to break up the ice over longer and longer distances. If you have steep waves, you get a very sharp transition. Thus you get breaking at the edge of the ice much more quicker. Here that was a limitation because the properties of ice in fresh water and so on, they're very difficult to control because you have no control of the flexural strength of the thickness a little bit. You can wait longer, but it is not so easy to extrapolate these results to a larger scale, and that's why we do the experiments at this moment. And that is the picture Alessandro sent me last night. I think it was around 5 o'clock there. So I think they're just, yesterday was day 3, so they've done one experiment, and then they were working on the next set and getting it ready to test today, I assume, and then we'll do again for next week ongoing experiments. That's it. Yeah.
Yes. Yours.
Can you estimate or quantify, let's say, the feedback of the wave propagation within broken ice in terms of amplification of the ice melting in the Arctic?
No, I will not, but it's definitely, I think that's a point, because if you have more overflow of water over ice, you have a larger area that is washed, and you will have faster melting. But personally, I do not know how much faster this is, but it is indeed a fact that the ice is melting faster with when the ice is broken, because you have much more exposure and more mixing and so on. So this is, but how much faster? It will also depend, of course, on the wave conditions. I am not aware of.
No, I'm thinking about some critical parameters that maybe you can test.
Yeah, but it is a very interesting question, but not an easy one to solve. And I think you have to couple. How would I say this? I don't think you can do it in a basin. It will be too difficult, but maybe it's possible to estimate it from larger scale experiments from satellite, and then couple these two wave conditions and try to get an estimate. But it's definitely a factor. But I cannot say where is the critical or whatever. I cannot tell you. I think the ice thickness was about 1 centimeter. I think. I'm not exactly sure. I'm not exactly sure if it was. I think it will be 2 in Aalto, but I think it was 1 centimeter in Melbourne. I would have to calculate because we know the steepness and we know the period, so we should be able to. But I think it's not big, that it's only a few centimeters. It's not.
In reality, if you have 1 meter ice thickness, but then you have 1 meter wave amplitude, it's too big wave for that.
No, well, I say a few. No, a few centimeters. Let's say 7-8 centimeters.
Yeah, but if
you have 1 centimeter.
Factor is 1 centimeter to 1 meter, let us say 100 times.
Mm-hmm.
So then in reality, you would have an amplitude of about 1 meter. That's quite big amplitude for the wave in ice.
Yeah, but this on the. If you look at the picture. Because once you're in the ice, the incoming wave is, let's say, 1 meter. Once you're in the ice, you drop down immediately to 15 or 20 centimeters.
1 millimeter. So how you can measure that? It would be wave in ice in relation to full scale. But it would be very small if the ice thickness is 1 centimeter.
Yeah, the measurements are done with cameras. You try to. I understand that the scaling is an issue. Also, the strength is an issue. But it's the mechanism as such does not change. I cannot tell you by hand the different scale factors. But it is the fact that you see that the ice is breaking and so on. It gives you the first ideas of the experiment. And that's the.
I think we could continue the discussion after. But thank you very much for the presentation. And I'd like to thank you all the presenters and just a small message.